So last time we proved that the fundamental domain for gamma 1 has this shape. So we have the circle here. Well, I'm very bad in drawing, right? So that's, I can do pictures nicely on the computer, but so this is rho, and this is high. This is minus rho bar. Okay, so it was this part. So this set corresponds one-to-one with the isomorphism classes of complex tori of dimension 1, as we see. So these are just C modulo a lattice. Now, this object is usually called the moduli space. The moduli space for the same thing, for complex torus of dimension 1. Now, first a word about the name moduli. Why is it called moduli? Meaning in English, to module out, it means to divide. But it's not the reason. The reason it's an Italian word, which is moduli. And the first one to study this type of object, they were calling the space of parameters or the space of moduli. So in Italian would be lo spazio dei parametri or lo spazio dei moduli for the object in consideration. So the word is actually coming from Italy. And so that's why I'm telling you. Okay, so as such, we would like to have on this set actually a bit more structure. A structure of a topological space, maybe a structure of a Riemann surface. And that can be done. And if I have time, after I finished everything that I really want to do today, I will also explain how can you put the topological and actually what is called a Riemann surface structure. A Riemann surface is a sort of space that Bas talked about to you today. It's exactly the same space, but you're doing everything over C. So it's, you don't want differentiable, you want holomorphic things. So it's exactly the same construction. You have to have an atlas, you have to have the chart and everything, but everything has to be holomorphic, not differentiable. So I would say, if I have time, I would say more about that later. But now we start with the real meat of the course. And so we give the definition of modular forms. So this comes in pieces, not all at once. First we start, we take k an integer. And we call a meromorphic function f from the upper half plane to C is weakly modular if well, I'll put it up because this is important. If what? If f of gamma tau it's equal to C tau plus d to the k times f of tau, where gamma is a, b, c, d. Oops. So if for all gamma in gamma 1, this is true. It's true, of course, for all tau in H. Okay. So it's a sort of, it's not really invariant in reaction, but it has a factor of automorphy. And the reason is that to have it completely invariant, it restricts too much. But also there is another reason. It is the following. If you take, if you do the differential of gamma tau, and this is the differential of A tau plus B, C tau plus D, then if you do all the computation, you end up that this is just 1 over C tau plus D square the tau. Here you have to do some computation. You just have to derive. So this means that if K is even, we have that f of tau f of tau d tau to the k over 2 is invariant under gamma 1 because here what you have, what you do the derivative, what you do, you take f gamma tau, d gamma tau, this is just c tau plus d to the k, c tau plus d to the 2 times k times over 2, d tau k over 2. And so it's just f of tau. So you get that these are the forms are invariant associated to the weakly modular function. Now, now we want to get to modular, so so not one thing. Here I take k even, and you say, oh, for k odd. Well, for k odd, there is not much to do, because if k is odd, and since minus 1 is in gamma, minus the identity, is in gamma 1, what do you get? You get that f of minus tau has to be equal to minus 1 to the k f of tau. So if k is odd, sorry? F of minus tau. Minus tau, it's minus tau. It's minus 1 to the k f of tau, and so if k is odd, the only solution is 0. Oh, sorry, yes, f of tau. F of tau is minus 1 to the k f of tau, yes. Thank you. And so there is no possibility. No, only 0. Okay. Now, to get to modular function, we have to see how this function behaves at infinity. So we have to express them also there. First of all, remember that we have two special elements. We have S, that is 0, minus 1, 1, and tau, that is 0, 1, 1, 1 in gamma 1. Oops. And if you remember correctly, I told you that these two generated gamma 1 bar. So to check, so f is modular, since minus the identity acts like nothing. F is modular if and only if it's sufficient to check it on these two. So f of tau plus 1 is f of tau, and f of minus 1 over tau is f of tau. Oh, so it's tau to the k f of tau. Okay? Now, this you can prove. It's enough to check it on those two. It's an exercise. So, what does this first condition tell us? That our function is, yeah. C? 1, 1, 0, yeah. Why I get it wrong? I should know this one. Yeah. Right, if not, it doesn't do it. So the first one is correct. So the first condition is this one. So f tau is equal to tau plus 1. Tells you that you can express this is in Fourier series, which means that you can use a new variable q equal to the 2 pi I tau, and you consider f tilde. It's just when you consider f as this, meaning f, instead of consider f of tau, you consider f tilde, f of tau, f of q. And f tilde is meromorphic in a disk of q q less than 1, let's say, with the origin removed. Now, if you have never seen it, the point is that that mapping, this is another exercise about this mapping. So you have the mapping tau goes into e to the 2 pi I tau. And if you take a strip, so this is what? E times A, E times B, and you call S, A, B is the strip here. So you have that is tau in C such that A is smaller than the imaginary of tau, that is smaller than B. And if you take a disk, an annulus, small r, big R, this is just an annulus. So this is big R, this is small r. Then this map, the map, it maps SAB via e to the 2 pi I times tau into the annulus E minus 2 pi over B, E minus 2 pi over A. So it maps strips into annulus. So the bigger you get the strip, the higher it goes, the smaller it gets the annulus, closer to 0. It never gets to 0, but so that's why f tilde is meromorphic into this disk with the origin removed, because you never get to the 0. Okay? This one also you can prove. So the behavior at infinity is going to be of our f is going to be the behavior at 0 of this f tilde. So we can give the next definition of modular forms. First, modular function. So, okay. So, so a weekly modular function is called modular if it's meromorphic at infinity. So when you consider the function as a function of Q, then when you go to 0, you have a pole. You cannot have an essential singularity. This means that when the imaginary part of tau grows, the function doesn't have an essential singularity there. And a modular function, which is holomorphic everywhere, including infinity, is a modular form. So modular forms are functions that behave in that specified manner with respect to the action of SL to Z, plus they're holomorphic everywhere, including infinity, when they are extended to infinity in that way. Now, finally, the last definition. F is a cusp form if it is 0, okay. Question? That this function is meromorphic at 0. The function that you consider, so f of e to the 2 pi I tau, which is f tilde of q, has to be meromorphic at 0. Okay. Oh, this is infinity, sorry, it degenerates. Sorry. So, of course, you would like to see examples. So let's try to see an example. The first example is done by Eisenstein series. So remember, we defined the Eisenstein series before. So remember, remember if we had a lambda, now lambda is just of the form z plus tau z. So we had an Eisenstein series that was the kth Eisenstein series. Now we just indicate it as a variable tau instead of lambda, as we did before. Is the summation over omega in lambda tau. Let's call it lambda tau. Lambda tau prime. When I put a prime means I don't take 0. So whenever I write something with a prime means without 0. Because there is 0 here, but I don't want it. And this is just omega. Okay, first of all, we have to verify. What do we have to verify? And what I claim, this is a modular form. What do I have to verify to have that this is a modular form? I have to verify the transformation formulas, and I have to prove that this one is a holomorphic function everywhere, including infinity. So it's a lot of things to do. Let's start with the transformation formula. Yeah? Sorry? I can't hear you. Oh, yeah, sure. 3 is okay, no? Yeah, it's 0, yeah, that's true. Okay, bigger or equal than 4. 3 doesn't count. But the series converges. So, the transformation formula. So we have to compute gk of gamma tau. What is this? This is the summation prime, so over m and n. And now I specify, so my omegas now will be, omega is m plus n. No, it's m tau plus n. And then I have what? I have 1 over m that multiplies a tau plus b divided by c tau plus d plus n to the k. So this is equal. Clearly, I can make the common denominator here, and so I can take out c tau plus d to the k. And then I get the summation of what? Over m and n prime of 1 over m a tau plus mb plus c n tau plus nd to the k. And this is equal c tau plus d to the k summation. Can you read down here? Can you read down here? Okay. Time summation of what? I can rewrite this one. 1 over ma plus nc tau plus mb plus nd to the k. I'm just reordering it. But now, ABCD, remember that gamma is ABCD and is in SL to Z, or gamma 1 as you want to call it. So these guys, where m and n runs over all the non-1, just run again over all the elements of the lattice. It's just another basis. We had the basis of the lattice that was 1 tau. We are just doing, meaning we are just redoing the thing over another. So it's exactly the same. You get exactly, this is just what you wanted to. Time what? gk of tau. This one runs exactly over the members of the lattice as did this one. You can convince yourself of that. So the invariant property is okay. Now for being holomorph. So now it has to be holomorphic as a function of tau. Here, again, there are some results of complex analysis that I either explain a bit later or just skip completely. So, holomorphicity. So we start with tau in the fundamental domain, not tau equal infinity. We have what? We have that M. So we have to show that that one. Oh, let me tell you the idea. So the main result that we are going to use, if not doesn't make any sense, is this one. If you have, because we are using some convergence results. So if we have a sequence, if we have a sequence of function, Fn, then the associated series so it's just the sum of Fn converges normally in D if for each point A in D, there is a neighborhood U of A such that no, a neighborhood and a sequence of numbers and a sequence Mn of non-negative numbers such that Fn of Z is smaller than Mn for all Z in D intersected with UA, and summation of Mn n equals 1 to infinity converges. So that's the normal conversion that we're going to use, because then things that are normally convergent, one can show that it's actually uniformly convergent. So, so what we want to do, we want to find we have to bound these terms, right? Meaning these terms we have to bound. So we take individually though. We take m tau plus n square. We are doing just for k even anyway, yeah? K even. The odd ones, they vanishes, of course. So we take this one. We want to bound this one in terms of something that doesn't depend on tau. So this one is what? This one is just m square tau tau bar plus 2mn real part of tau plus n square. So to bound 1 over this, we have to bound from above, we have to bound this one from below. So this one is bigger or equal than m square plus minus m times n plus n square. Okay, and this is just exactly m times rho plus n square. So we have that 1 over m tau plus n is smaller or equal than 1 over m rho plus n. And this one converges, meaning the series of now you can put k. Here you have Here you have k as well, and here you have k. This one converges. So it defines an holomorphic function by this principle. Next, we have to look at infinity. So to show that it's holomorphic at infinity, it suffices to show that it has a value at infinity. So we will just compute the limit. So we compute the limit as the imaginary part of tau goes to infinity of gk of tau. Now, as I said, this normal convergence implies uniform convergence. So we can we can switch the limit and the sum, so we can compute each individual limit. So we can compute limit of any single piece, so limit of 1 over m tau plus n k as imaginary part of tau goes to infinity. Oops. So if m is different from 0, that limit goes to 0. Oops. While if m is equal to 0, you get what? The limit I'll write m tau, but just this is just 1 over nk. So in the end, the value at infinity is just a summation for n 1 over n to the k. And this is a very famous function. This is the Riemann zeta function. And so this is just zeta. Oh, it's twice, sorry. Because I take n can be positive and negative, so it's twice this one. Because here I'm summing, what is gk? I forgot. Let me write gk here is the sum over m and n. 1 over m tau plus n to the k. So I'm summing here, these are in Z2. So it's positive and negative prime. So here n. Okay. And k is even, so you don't have to worry. K is even, so if it's negative, still you get the same value. So this is just the Riemann function computed at k. Okay. So we have an example of a modular form. Now, Marussia will do more. She will compute the dimension of this space, of the space of modular forms. But in order for her to do that, she needs a formula that we're going to prove. And it fits well in this part because we have it's an application of the theorem of residues. So it's precisely what we have been talking about. Okay. So, theorem. We take f, a modular function of weight k, not identically 0. Then the order at infinity of f. This is just the order of f tilde at infinity, plus 1/2 the order at I of f, plus 1/3 the order of at rho of f, plus the summation over p in f. I'll tell you what the star means of the order of p at p of f. It's just k over 12. And the star means I'm summing p in f, so p different from I and rho. So I'm summing on all the other points. Now, we want to prove this one a little bit, let's say. Okay. So what do we do? You remember how do we get this? If I have a contour, right? What do I have to integrate? So to get the sum of the orders, I have to integrate 1 over 2 pi I, the integral over a contour of f prime over f in the tau. It's equal to the summation of whatever is inside. So let me write. Let me give you the picture. So we have this way. Here we go like this. And we have, of course, the picture is not perfect. So we have A, B. Here there is rho in the middle. This is B prime. This is C, C prime. Here there is E. Here there is minus rho bar. Here there is D. And this is D prime. And this is E. So if we integrate, we call this one C. If we integrate along this, and the orientation is like this. If we integrate like this, we just get the sum of the residues inside here. Correct? So this we get just the sum P in F star. Sorry, the order of P of F. So the idea is we have to compute this side. Okay? If we compute this side, then we can equate the two, and maybe if the left side can be expressed in terms of this guy, we get the solution. Now, first of all, note that I'm assuming no zeros or poles on the boundary. we will see, we can discuss later how to do if there is something on the boundary, meaning here, or here, or here, or here. So, one thing should be clear. If I integrate, if I do the summation of the integration here and here, what happened to that thing? If I do integral 1 over 2 pi I from A to B plus the integral from D prime to A this is 0. Okay? No, it's not, sorry, it's not 0. I went ahead of myself, sorry. Let me erase it. I just wanted to be smart, but I just went ahead of myself. Let's start in order. Let's start for the first, from the top. Oh, from the side, what we want to start with. Let's start from the integral from E to A. So we start with the top, with this one. Okay. Well, how do we can compute this one? This is just, if you think about it, this is for the f tilde, so the function for the, as a function of q. This here is just a circle around 0. So if we move it to q variables, this is just a circle, here it's 0. So the integral for the residue theorem just gives you the order of f at infinity. So this one gives you for the residue, meaning application of the residue, this gives you, and note that we are going in the opposite direction, so we get a minus. We get minus the order at infinity of f. Next. Next, I want to integrate on this little guy here from B to B prime, this little circle, and here it is rho. So the integral from B to B prime of f 1 over 2 pi I f prime over f. Okay, if I do the full circle, what do I get? Like there, I get, if I do the integral, if I compute the integral over, so let's say we complete the circle here, and we call the circle completed C0. So the integral over C0 of 1 over 2 pi I f prime over f, the f, this is just, again, we are going in the wrong direction. We are going clockwise, not counterclockwise, so we get a minus the order at I of f for the same theorem. Now, this one, what we can say that if we shrink, if we make this with smaller and smaller radius, so as b prime goes to 0, this one goes to what? Well, the angle between b and b prime is going to be pi over 6, so this goes to minus 1 over 6 to the order of in I of f. We are just getting that portion of the integral. Sorry? I can see you. Sorry, no, a row, right, completely correct. Yeah, I don't know why I said row. Thank you. Yeah, of course. So you're just shrinking and shrinking and shrinking. The value is always this one, so you're getting just a sixth. When it gets very small, it tends to 1/6 of that value. You cannot say there is a sixth here because the function can do weird things, but in the limit, you get a sixth. And of course, you can see immediately that these ones go exactly the same. So it's exactly the same argument. So the integral from, what do I have? C, did I put a C prime? I forgot the C, B prime, C prime. From C to C prime, 1 over 2 pi I, f prime over f, the tau goes to, again, when C prime goes to 0, it tends to minus 1/2 the order at I of f, and for the one on the other one, so d prime, here d prime goes to 0, it goes to, again, minus 1/6 the order. And now the order is the same, right, because these are conjugate, the order of at rho of f. Because this one is exactly the same as the order, because the function is modular at minus rho bar of f. Okay. Now, no, as I said, these two integrals cancel out. I was correct. I don't know why I was doubting myself. These two integrals cancel out. They are going in the opposite direction. And the only thing that we are missing is the integral from here and the integral here. So let's see how we can compute those. Here. Here you have to use that. What's the relation here between this part and this part? So you can move from one to the other by applying S. So you move from here to here by tau goes in minus 1 over tau. So, and we know that f of S of tau, it's equal to tau to the 2k. And so we get that df of tau over f of tau, it's equal to k d tau, d tau over tau. So in the end, what you get that the integral 1 over 2 pi I from b prime to c, this is f prime divided by f, the tau, it's plus the integral from c, b prime to c, c prime to d, this is just the integral from b prime to c of df over f. And this is just 1 over 2 pi I minus k d tau over tau, and this is just minus k times 1 over 12. Okay? Now, if you put all together, you get the formula. You have the various pieces. You have twice minus 1/6, minus 1/6, you get 1/3, you get the minus 1/2. Here you have the minus 1 over 12, so the formula is there. It's a lot of integral computation. Oh, Now, just a word. If you have zero or poles on the boundary, for example, you have a pole here, what do? Well, you just go around it, right? You do like this, and you do like this, and you do the same computation. So the poles appear only once, and everything, it's again the same, okay? And unfortunately, I have no more time, so I cannot tell you about the topological structure on the modular space. Thank you very much.